Um, Hello, everyone. Thanks for coming to our talk. Super excited. I'm Cheng, a software engineer from Databricks. I'm also a committer of Apache Spark and Apache Parquet. Today, my colleague Vida and I will co-present you some of our experiences and best practices about data layout. So, Vida.
Great. Let's start to give you just a little bit of an introduction of the company. So I think a lot of you have heard of Databricks, but Databricks was actually co-founded by the creators of Apache Spark. And Spark was created in 2009 at the UC Berkeley AMP Lab. Our mission is to make big data simple, and our product is actually the Databricks platform, which hopefully a lot of you have used. At the end of this talk, I will, if you like what you see today and you want to try out and test out some of these things that we've seen on Spark, I will show you how to sign up for our community edition.
Thanks. All right, then let's start. So as we already knew, Apache Spark is a very powerful framework, but it's a framework with some temper. It's just like a Super Mario. If you provide him the right ingredients, it powers up and gets much more efficient. And if you keep doing so, he even knows how to Spark. However, if you serve him the wrong dish, then things can be pretty embarrassing sometimes. And also, sometimes it can be pretty messy. So in terms of Spark, what is the food you really serve to Spark? That's your data, right? Okay. Then how should we organize our data so that Spark can leverage those data and accelerate our workflows and make everybody happy? So now we're going to share with you the recipes we serve Spark at Databricks. So firstly, Vida will discuss her experiences in file formats, and later I will provide some more information about directory layout and some other best practices. Okay, Vida.
Great. So what you'll notice about today's talk is we're not actually going to go through Spark code. We're teaching you how to optimize Spark by how you lay your data out and actually save it. And that is, honestly, 80% of the game of efficiency for Spark is choosing file formats that are good, choosing the right file sizes, choosing the right partitions, and other things. So it has nothing to do with code, just how you lay out your data within Spark. So first, let's talk a little bit about choosing a good compression scheme. So obviously, the characteristics you want to look for in a compression scheme, the higher the ratio, the more your data compresses, the better that's going to be. Obviously, that's what you're looking for in compression. But you're also trying to trade that off with how much time it takes to encode and decode your data as well. So some of those are some of the trade-offs that you have with different compression schemes. The other thing that you want to think about when you're talking about compression is thinking about whether your compression format is splittable or not splittable. So it definitely, if it's splittable, it affects the amount of parallelism you can get on a single file. So if the file format is splittable, that means two different tasks in Spark could actually go at the same file at the same time. If it's not splittable, then you're always going to have an issue. So some of the common splittable compression schemes that we see are LZ4, Snappy, bzip2, LZO, and there are others. Those are typically ones you're going to choose for big data. gzip we see very common within Spark, even though it's non-splittable. You only need to choose a compression format that's splittable if your file size is really, really large. So if you keep your file sizes under a gigabyte, then you'll always only have a single task look at that single file. It's not as important. So when it's really important to have a splittable file format, it depends on your file sizes. So definitely one of the slowest things that Spark can't do is if you have one giant 1 terabyte file that's completely unsplittable. We've seen that before, right? So that there's no way that Spark, you're going to be able to have different nodes process that or anything. It's just a single Spark driver that's going to read that, and it's going to fall over when it gets to that 1 terabyte. You're going to end up having to use some kind of decoder that goes disk to disk on that. So just keep that in mind. If you keep your file sizes under 1 gigabyte, you can choose non-splittable formats like gzip that are fast, that have good compression speeds. But otherwise, if you have those file sizes beyond a gigabyte, make sure you use one of the splittable file formats. Anything else you want to add about compression schemes?
So actually, gzip is still applicable for Parquet because Parquet usually, a Parquet file consists of multiple row groups, and those compression schemes are always applied at the level of row group level. So whatever compression scheme you choose, Parquet files are always splittable. This is why we mentioned here that gzip is still applicable for Parquet.
Great. So actually, how many people have worked with Parquet files here? This is great, and this is definitely something that we've seen. So Parquet is the recommended file format for Spark SQL. Definitely before, we didn't see that people were using Parquet. More and more so we see nowadays that people almost always use Parquet. And as Cheng mentioned, the reason why Parquet is so wonderful is because it's a columnar format. So you'll never collect data in Parquet or a columnar format, but you'll also sometimes ETL it into a columnar format to make it easier to query. So oftentimes when you do a Spark SQL query, you're only ever grabbing a couple columns at once. That is a lot easier to do with a columnar format where you're only reading one part of the file than if it's all over the place. The other advantage of a columnar format is you don't have to parse the data file all over again to get the structure out of it. So, let's talk about a non-columnar format file like CSV. There's a lot of overhead to not just reading the entire file, but figuring out where the end of line characters are, parsing out the different columns and fields before you grab a couple of those. So CSV is many, many, many times slower for common Spark SQL queries, and you can time that. Like I've definitely seen queries be 10 times faster or even less if you just choose Parquet as opposed to CSV to read your data. So there are some newer kinds of columnar formats as well, ORC and Carbon data. I'm less familiar with that. Maybe Cheng can tell you a little bit about those file formats.
Yeah, Apache Carbon data is a project initiated by Huawei, and that is also a very smart and analytics-friendly columnar file format, and also Spinach, which you might already heard about the talk previously by Daoyuan Wang from Intel today, and it's also another columnar format from Intel.
Great, and since Parquet is such a great file format, we wanted to call that out in particular. We really recommend that you check out the Parquet website and watch some of the YouTube videos and understand why Parquet works so well. So it turns out that Parquet actually oftentimes gives you the best of both worlds, where it compresses really easily, as well as the time to encode and decode is also really, really fast. And that's just because they've really exploited the fact that there's a columnar format, you understand the types that you're working with or other things. So from a research perspective, just learning about it, the geek in you will be very happy if you go look at the YouTube videos on Parquet. So next, let's talk about semi-structured text formats. So what we're talking about is like JSON and CSV. So what we mean by JSON and CSV is that they have a structure to it, but you have to kind of parse that out a little bit more. So let's talk about JSON. So JSON is something that's supported by Spark out of the box. However, there's a little bit of a caveat here, which is to work with the Spark JSON library, you do have to have one JSON object per line. So if you start to split out your JSON objects by multiple lines, you'll have to manually parse the JSON object yourself. That's not fun to do. So when you write out JSON, do one JSON per line. JSON has a complex data structure, so Spark can work with the nested types that you have in JSON, and it can even infer the schema by looking at a number of different objects within JSON. Also keep in mind that Spark is smart, so if it finds that some of your records are malformed, it'll collect it into a corrupted record column, and then all the other fields are set to null. Let's talk a little bit more about JSON in terms of things to watch out for. So one really important thing about JSON when you're using it with Spark is that Spark SQL can do schema inference on the JSON objects. So it can actually go through your file, read every single one of your JSON objects, and figure out what the superset of keys are, and then create your structure from there. So if you want JSON to read in fast and you know what the the structure should be, you can make when you're working with JSON, you can make it go a lot faster by programmatically specifying your schema. And you can do that by just reading in a single JSON object and then grabbing the schema from that and doing it. Any other tips about schema inference with JSON?
Yeah, so schema inference is pretty good and handy for exploratory tasks or interactive tasks. However, schema inference sometimes can be inaccurate and unreliable. For example, it may guess the wrong data type. So whenever you use JSON data source of Spark in production, always specify an accurate and exact schema that you really want it to be.
The other thing about JSON to watch out for is when you have hash maps in part of your JSON files, make sure that the keys that you have are a finite number of things. Yes. So I've seen sometimes people have the key be a UUID, and then that job will fall over. Because what Spark will do is it'll try to infer the schema, and it'll keep adding that UUID as part of that key, and then eventually blow out and have an out-of-memory error. So the way we got around that for our particular customer was they had to detect that UUID, and then split it out and actually have the key be, the key be the word key with the UUID, and then have the value be the value that was there. So just make sure that your schema is a finite schema. Great. Let's talk next about CSV. So CSV is really, really common just because it's an easy to use column format. There's a lot of BI tools and other things that will automatically output data as CSV for you to use. So CSV, there are lots of optimized packages now. So in the earlier Spark days, you might have used some kind of Hive CSV parser. You should use the Spark CSV package that's developed by Databricks within Spark data frames now that should come by default to analyze your CSV files. We've made a number of optimizations there to read it. For CSV, it will not handle structured data, so it will again just be a single field, and you can look at different separators and other things there for CSV. I mean, I like CSV format. It's oftentimes a good file format to collect your data in. When you actually run SQL queries against it, if performance is really, really important, it's worth the overhead of transforming it over to Parquet, though. I also really commonly see it as a way, if you have a data frame, people write out to CSV so that they can then input it into a BI tool.
Yes.
Any other tips you want to mention about CSV?
Yeah, so at the first side, CSV looks pretty simple. It's just some fields separated by commas, but actually there isn't a common specification or standard of the CSV format. So it's not really recommended to be the final artifacts of your ETL pipeline. And we saw, according to our experiences, it's mostly for legacy data providers and consumers, so that you have to read CSV or have to produce CSVs, then you use CSVs for this kind of purposes. Yeah.
Great. And then there are times where you're still going to need to read raw text files in. So there is a spark.read.text command that you can use to do that. Keep in mind to keep the file size under 1 gigabyte, as we mentioned, if you use the non-splittable compression scheme. So that's just general good practice. And make sure that with your raw text file, since it's completely unstructured, you handle all the corner cases for how the files might come out. So you can use if you have malformed lines, there's two ways you can get around it. You can use a filter transformation to drop the bad line, or you could use a map transformation if you wanted to try to actually fix the bad line. And if you're not sure which, you can also use a flat map that will allow you to take the line and figure out if you can recover it. If that's the case, then you will rewrite the line, and if not, then you'll just output an empty array to drop it. Great, on to the next topic.
Okay, thanks Vida for the excellent summary. And next, I'm going to talk about my experiences and about directory layout. Okay, so Hive users may already be pretty familiar with partitioning. So in short, partitioning is a kind of a feature that enables coarse-grained data skipping optimization. So the figure on the right shows a partition data set with 2 partition columns, year and genre. So for each distinct value, of each partition column, a directory is created to hold all the data belonging to that partition. And Hive users may agree that partition management can be pretty tedious since you have to keep the actual data and the metadata stored in the metastore synchronized. To address this kind of pain point for exploratory and interactive scenarios, we implemented a partition discovery in Spark so that you may just drop in your raw file directories and Spark will try to figure out what the partition columns are and as well as their data types, which is pretty handy. But similar to the case of Schema Inference for JSON and CSV, this kind of automatically inferred schema can be sometimes inaccurate and unreliable. So still, always specify an accurate schema when you are using this kind of feature in production. So creating a partition table is pretty straightforward in using either SQL or the data frame API. So here we create a ratings table from a music table partitioned by the columns year and genre. And you can see that we just specify the column names in the partition by clause and it's done. So different from Hive, Spark by default uses dynamic partitioning so that you do not need to specify individual values of individual partitions and it saves lots of work. So why bother? Why do we really need partitioning stuff? So how can this be useful? So the secret here is partition pruning. When Spark finds there are some simple file predicates in your query, it tries its best to prune partition directories that definitely don't contain the data that you are searching for. And that's why it's called coarse-grained because it works on the directory level. So here are some examples. These three filter predicates are very friendly to partition pruning. So for the first one, the first two predicates are both conjunctive predicates, and for the first one, both components are comparing a partition columns with a constant. And the second one, we can leverage the first component and just ignore the second one and apply the second filter predicate later. And for the third one, although it's a disjunctive predicate, we can still leverage it because both components are only referencing partition columns. On the contrary, these two predicates are not very friendly to partition pruning because for the first one, it's a disjunctive predicate containing a non-partition column. And for the second one, we are really comparing a partition column with a non-partition column. Okay, so here are some tips for partitioning. So when you are using a partition table, try your best to avoid excessive partitions because this stresses metastore for persistent tables, which means you have to persist every single partitions into the metastore. I mean, you have to partition the metadata for every single partitions into the metastore. And also, this stresses the file system when you are reading directly from the file system. And so here are some suggestions. Firstly, avoid using too many partition columns. So according to our experiences, maybe just less than 5 partition columns is usually pretty good for most use cases. And also, try avoid using those partition columns containing a large number of distinct values. And for example, instead of using the first name of your customers as a partition column, try to use the first letter of their first name as the partition column so that you can reduce the number of individual partitions. Also, in Spark 2.1, we try to address the problem of large partition tables with a huge number of partitions. So although I just mentioned that we should try to avoid those kind of scenarios, but this kind of table are really inevitable in some cases. So in Spark 2.0, we persisted every single partition into the metastore and pushes partition pruning into the metastore. In this way, you do not need to perform partition discovery every time you read the table from Filesystem for the first time during your Spark session. And also, you do not need to pull all the information about every single partitions out of Metastore and do the filtering inside Spark. So please check out our engineering blog post for more details about this feature. And the second one is bucketing. So bucketing is a pretty interesting feature. A bucketed table actually pre-shuffles and optionally pre-sorts the data inside this table. And in this way, the layout information can be persisted into the Metastore, and our Spark SQL query optimizer can leverage this kind of information to make a better query plan to avoid shuffling and sorting when joining super large data sets. For example, let's say we are joining two big data sets and with the column K as the joining key. And if we already build these two tables using bucketing and partition those two tables using column K, then we do not need to shuffle these two tables so that we can repartition them on column K, and this can save us a lot of time during runtime. And since the layout information has to be persisted into Metastore, this feature is only applicable for persisted tables. And creating bucketing tables is also pretty straightforward. Basically, you only need to mention which column you want to bucket and how many buckets you want. And also, optionally, you can also specify a sorted by column class. And here is an interesting experience. When you are using bucketing together with columnar format, you can gain much more performance benefits. So the reason is that bucketing, as we just mentioned, can be used to sort the data within every single bucket. And for columnar formats, like Parquet and ORC, they come with efficient data skipping features based on the min-max statistics. And this kind of data skipping feature works best when we are searching columns that are sorted. For example, here is a simple diagram for the Parquet format. So within a Parquet format, a file usually consists of several row groups, and within each row groups, it consists of multiple column trunks, which consist of row data in columnar format. So let's consider column 2 here, and assuming that column 2 is already sorted, then you can see that we can find the min-max data in this Parquet file. Now let's consider we are searching for values greater than 200. According to this statistics, we can just drop the first and the second row groups because these two row groups definitely don't contain the data we are searching for. And that is how bucketing works with columnar formats. And next, I'm going to discuss about some other best practices about Spark. The first one is file size and compaction. So as we all know, small files are not welcome in the scenario of big data processing because they cause excesses and parallelism. For example, we usually create one task for one single file, and if the file size is too small, like 1 KB or something, then you're really wasting your cluster resources. And also, it causes extra file metadata operations, and this can be particularly bad for files hosted on S3 because metadata operations on S3 can be pretty slow. For example, if you are just checking whether a file exists, it takes like 200 milliseconds. Then how do we control output file sizes? In general, Spark produces one file for every single task in the final output stage. So if you want to control the file output size, what you really need to do is just to tune the parallelism of the output stage. So usually you can do either coalescing or repartitioning. And repartition is usually considered very expensive because it introduces an extra shuffle. However, repartitioning preserves high parallelism for upstream tasks and stages, and so that when these stages are computation intensive, you still get the benefits of a higher parallelism. And on the other hand, you still have small output files for the final stage. And here is a true story. One of our customers was complaining that Spark ORC read performance is much slower than Parquet. So at the author of Spark Parquet integration, I'm pretty happy that Parquet is fast, but maybe not that fast because the same query took only 3 seconds on the Parquet dataset, but 4 minutes for an equivalent ORC dataset. There had to be something wrong. So what I did to investigate this issue is that I ran just a simple count star query, and that one took just a few seconds on the Parquet dataset, but took 35 minutes on the ORC datasets, and it issued tens of thousands of I/O requests. So most task execution threads are just reading ORC stripe filters, and that's pretty weird. So, sorry.
We just have 3 minutes left, sorry.
And here is a simple diagram for ORC file formats. So as you can see, similar to Parquet, it also consists of chunks of columnar data, and usually the stripe filter should only take very few space in the ORC file. But on the contrary, those task execution threads are blocked on the reading stripe filters. Then just run this snippet. Basically, it tries to count the number of stripes within every single ORC files. And what I found is pretty interesting. There are like 1,000 files. Most of them are super small, like 1 KB or even smaller. And a handful of them are like are a little bit larger, 15 megabytes or so. And but there are like 1,400 ORC stripes within each of these 15 megabytes files, which means these malformed but not corrupted ORC files causes extra I/O requests to S3. Basically, you need to issue over 2,000 read requests to S3 to read merely 15 megabytes data. So that's even worse than CSV, so not mention Parquet. But why do our customer hit this kind of issue? Because tiny ORC files were generated by those streaming jobs, resulting one tiny ORC stripe inside each ORC file. And the filters might take even more space than the actual data. And then our customer also realized that the small files are not ideal, so they tried to compact those small files, but they used the wrong command. They were using the Concatenate command provided by Hive. However, the Concatenate command just concatenates the small stripes and forming a larger ORC file. It doesn't break the boundary of those stripes and resulted in the previously mentioned malformed ORC files. So lesson learned here is that never write small files in columnar format. So for streaming jobs, use CSV or JSON as an intermediate output, and then compact them into larger Parquet files later, so that you can get better write pass performance as well as better read pass performance.
1 minute.
Okay. The second tip is schema evolution. So columns come and go, but never change the data type of a published column. This is because if you do that kind of thing, you may have two files with columns of the same name but different data types. And file formats like ORC and Parquet may fail to merge the schema and consider this data set as corrupted. Okay, so that's another true story which became pretty messy. So our customer shouted at us that we have a Parquet data set which is corrupted. And what really happened is that the original schema is 2 columns of decimal and int, but accidentally they wrote some other data where both columns become double. And all those files were written into the same directory. Therefore, Parquet sees these 2 kinds of different schema, and cannot really merge them. And although every individual Parquet files are contact and good, but as a whole data set, this table itself is considered as corrupted. So, so the cure here is pretty simple. We just filter out all those files with the wrong schema and try to fix all the schemas and rewrite them. This can be pretty exhausting because all the files are appended into a single directory. The lessons learned here is that, firstly, be very careful on the right path because you can accidentally change the schema. The second is that consider partitioning whenever possible. Firstly, for better read performance due to partition pruning, and secondly, it will be easier to fix corrupted data when something really bad happens.
We're sorry that we didn't leave time for questions, but if you go to this Google slide, if you do post a question, we will make sure to answer it on that same slide there. So as I mentioned, if you guys are interested in trying Databricks, we have a community edition that you can try for free. So just go to databricks.com and sign up for a community edition account. It's totally free for a developer. And then we also have an early release of the Spark Definitive Guidebook if you want to download that, and we highly recommend that. Go.databricks.com/book.
Okay, thank you very much.
Thank you.
Okay, thank you guys.